Another example, here's some other distribution. I don't know what it's called. Maybe you can find it in the book. I'm not sure. Let's suppose that y1, y2, etc., y through yn are independent random variables. They can be a random sample from a distribution with this kind of a density function. By the way, if you're not familiar with this, this is an indicator function. We use these oftentimes. They come in handy. If I have a statement in here, then this evaluates to be 1 if statement is true, and 0 if the statement is false. Okay? And this is called an indicator function. It's a 1 or a 0. Okay? It's a nice, convenient way of telling you that, you know, if these two things, if everything in here is true, then this density function looks like this. If any of this stuff is not true, then the density function is 0. Okay, so let's find the maximum likelihood estimator of theta in this case. So I'll write down my likelihood function of my values given theta. This will be the product of f sub yk given theta, k equals 1 to n. In this case, this will be 1 over theta to the n times r to the n times the product of, let's see, k goes from 1 to n of y sub k to the r minus 1 e to the negative yk to the r, all over theta in the exponent there. Okay. Now, remember, the idea is you want to differentiate all this stuff. Well, that's going to be kind of messy because you have this huge product. So let's take the logs. Okay, let's take the logs, and I'll get the log likelihood function. Can I just say log of L is, well, let's see. So if I just do this first part, this is going to be the log of r to the n over theta to the n. That's going to be n log r over theta, isn't it? And then plus, remember the log of the product is the sum of the logs. So I'm going to add to it. Looks like it's going to be the sum, k goes from 1 to n of the log of y sub k to the r minus 1 times e to the negative yk to the r over theta. Oh, I'm missing my indicator function stuff here, right? Can I just abbreviate it like that? Okay, just put it out to the side there. And so this will be, okay, so if I take the log of this stuff, if this stuff is 1, log of 1 is 0. So I really don't have to worry about all that stuff. Let's see. So this will be n log r minus n log theta, right? And then plus, let's see, what do I have going on inside here? I'm taking the log of all this stuff, right? So it'll be the sum, okay, goes from 1 to n. I have the log of the product is the sum of the logs, right? So I have r minus 1 times the log of y sub k, and then the plus, the log of all this stuff. Log of e raised to all this stuff. This is just the exponent, so it's going to be, it's actually going to be negative y sub k to the r over theta. All right. So at this point, I think I can start thinking about taking the derivative. Okay, so I'm going to say the derivative with respect to theta of my log likelihood function is going to be, well, this first term is constant with respect to theta, so I get a big fat 0. This stuff is going to be negative n over theta, right? Minus, I guess, the derivative with respect to all of this stuff is going to go away. So, right, so I'll have, wait a second, I get the minus sign, yeah. Minus sign comes from here. There are no thetas in these terms, right? So I'll have minus some k goes from 1 to n. This minus sign is coming from here, right? Should be derivative with respect to theta of y sub k to the r over theta, right? And so this will be negative n over theta minus sum k goes from 1 to n of 1 over theta squared positive, there we go, y sub k to the r, okay? Or just negative n over theta plus 1 over theta squared sum y k to the r, k goes from 1 to n, okay? So then setting this to 0, I get that n over my maximum likelihood estimator for theta, MLE, okay, equals, right, 1 over theta hat MLE squared times the sum, k goes from 1 to n of yk to the r. If I multiply through by theta hat MLE squared, I get, and then divide by n, I get that here's my solution. So this is my maximum likelihood estimator for theta in this case.